You think you've seen bad weather. You think you've experienced what nature can throw at humanity. But what if I told you that there was once a period on Earth when it rained continuously for 2 million years straight? Not days, not weeks, not even decades. 2 million years of relentless, catastrophic rainfall that fundamentally changed the face of our planet forever. This isn't science fiction. This isn't some Hollywood disaster movie. This is the Carnian pluvial episode, and it's the most extreme weather event in Earth's recorded geological history. An event so devastating that it triggered one of the largest mass extinctions our planet has ever witnessed, reshaping evolution itself and setting the stage for the rise of the dinosaurs. But here's what's truly terrifying about this story. The same geological processes that triggered this ancient catastrophe are happening again right now, and the parallels to our current climate crisis are more disturbing than you might imagine. I'm about to take you on a journey back 232 million years to witness the most incredible meteorological nightmare our planet has ever endured. By the end of this video, you'll understand not just how this happened, but why it matters more than ever for our future. We're going to explore the science behind this ancient apocalypse, uncover the shocking evidence that proves it really occurred, and reveal what it tells us about the terrifying power of runaway climate change. But first, let me paint you a picture of just how unimaginable this event really was. Imagine stepping outside your door every single day for your entire life and seeing nothing but rain. Now imagine your children doing the same thing, and their children, and their children's children. For 66,000 generations of human lifespans, the skies never cleared. The sun became a forgotten memory. The Earth transformed into something completely alien. This is the story of when our planet nearly drowned itself, and it starts with a geological catastrophe that makes modern volcanic eruptions look like birthday candles. During the late Triassic period, Earth looked nothing like the world we know today. The supercontinent Pangaea dominated the landscape, stretching from pole to pole like a massive scar across the planet's surface. The climate was already hot and arid, with vast deserts covering much of the interior. But beneath the surface, something was stirring that would change everything. In what we now call the Wrangellia province, stretching across parts of modern-day Alaska and British Columbia, the Earth's crust was preparing to unleash hell. Massive volcanic systems were building pressure, fed by enormous magma chambers that had been accumulating molten rock for millions of years. These weren't ordinary volcanoes. These were flood basalt provinces, geological monsters capable of covering entire continents with lava. When the eruptions finally began, they didn't stop. For millions of years, these volcanic systems pumped unimaginable quantities of carbon dioxide, sulfur compounds, and other gases into the atmosphere. We're talking about volcanic output that dwarfs anything in human experience. The Yellowstone supervolcano, which scientists consider one of the most dangerous geological features on Earth, would have seemed insignificant compared to what was happening during the Carnian. But here's where the story takes a fascinating turn. The volcanic emissions didn't just heat up the planet directly, they triggered a complex cascade of atmospheric and oceanic changes that created the perfect storm for the most extreme precipitation event in Earth's history. The massive injection of carbon dioxide into the atmosphere created a super greenhouse effect. Global temperatures soared to levels that would make our current climate change concerns seem modest. But temperature wasn't the only factor. The volcanic emissions also pumped enormous quantities of sulfur compounds into the atmosphere, creating aerosols that affected cloud formation and precipitation patterns in ways that scientists are still trying to fully understand. As the planet heated up, the hydrological cycle went into overdrive. The warmer atmosphere could hold vastly more moisture than before. The oceans began evaporating at unprecedented rates, loading the atmosphere with water vapor. But the changed atmospheric chemistry meant that this moisture didn't just fall as normal rain. It created a feedback loop that sustained continuous precipitation for geological ages. The evidence for this incredible event is written in rocks around the world, and the story they tell is almost too extraordinary to believe. In northern Italy, paleontologists have discovered sedimentary layers that preserve a record of this ancient deluge. These rock formations show clear evidence of massive flooding, dramatic changes in plant and animal life, and chemical signatures that can only be explained by prolonged, intense rainfall. But the Italian evidence is just the beginning. Similar geological signatures have been found in locations across the globe, from China to North America to Argentina. The consistency of these findings across different continents provides overwhelming evidence that this wasn't a localized weather phenomenon. This was a global catastrophe that affected every corner of the Earth. One of the most compelling pieces of evidence comes from the fossil record itself. Before the Carnian pluvial episode, terrestrial ecosystems were dominated by specific groups of plants and animals that were well adapted to the hot, dry conditions of the time. But the fossil record shows a dramatic turnover during this period, with many species going extinct and entirely new ecological communities emerging. The plant fossil record is particularly revealing. Before the Great Rains began, the landscape was dominated by drought-resistant conifers and seed ferns. But during the Carnian pluvial episode, these plants largely disappeared, replaced by moisture-loving species that could thrive in the perpetually wet conditions. The change was so dramatic that paleobotanists can identify the exact geological layers where the transition occurred. Even more fascinating is what happened to the animal kingdom during this time. The prolonged wet conditions created vast new freshwater habitats, allowing aquatic and semi-aquatic species to flourish and diversify. At the same time, many terrestrial animals that were adapted to dry conditions faced extinction. The fossil record shows a complete reorganization of ecological relationships during this period. But perhaps the most significant consequence of the Carnian pluvial episode was its role in setting the stage for the rise of the dinosaurs. Before this event, dinosaurs were relatively minor players in terrestrial ecosystems, competing with other reptilian groups for dominance. But the massive environmental changes triggered by 2 million years of rain created new ecological opportunities that early dinosaurs were uniquely positioned to exploit. The extinction of many competing reptile groups during the Carnian opened up ecological niches that dinosaurs rapidly filled. Their more efficient respiratory systems and potentially superior adaptability to changing environmental conditions gave them crucial advantages in the post-deluge world. Within a few million years after the rains finally stopped, dinosaurs had become the dominant land animals, beginning their reign that would last for over 160 million years. The chemical evidence for this ancient catastrophe is equally compelling. Scientists analyzing ancient rock formations have found distinctive isotopic signatures that indicate massive changes in the carbon cycle during the Carnian period. These chemical fingerprints show that enormous quantities of carbon were being cycled through the atmosphere and oceans, consistent with the kind of extreme volcanic activity that would have triggered the prolonged precipitation. Researchers have also discovered evidence of dramatic ocean acidification during this time, caused by the absorption of excess atmospheric carbon dioxide into seawater. This ocean chemistry crisis contributed to marine mass extinctions that paralleled the dramatic changes happening on land. The seas became more acidic than they had been for millions of years, causing the collapse of many marine ecosystems. Temperature reconstructions based on geological evidence suggest that global average temperatures during the Carnian pluvial episode may have been 10 to 15 degrees Celsius higher than pre-industrial levels. To put this in perspective, current climate change projections worry about temperature increases of 2 to 4 degrees Celsius. The Carnian warming was in an entirely different league, creating atmospheric conditions that were truly alien by modern standards. The atmospheric composition during this time was also radically different from anything in human experience. Carbon dioxide levels may have reached concentrations of 2,000 to 3,000 parts per million, compared to today's level of just over 400 parts per million. These greenhouse effects that sustain extreme atmospheric conditions created a supered the intense hydrological cycle for millions of years. But what's truly remarkable about the Carnian pluvial episode is how it demonstrates the incredible sensitivity of Earth's climate system to changes in atmospheric composition. The volcanic emissions that triggered this event injected carbon dioxide into the atmosphere at rates that were probably similar to what human industrial activity is doing today. The difference is that the Carnian emissions continued for millions of years, while human emissions have been accelerating for only a few centuries. This parallel raises some deeply uncomfortable questions about our current trajectory. If relatively modest changes in atmospheric chemistry could trigger such extreme and long-lasting changes in Earth's climate system 232 million years ago, what might happen as we continue to alter atmospheric composition at unprecedented rates today? The Carnian pluvial episode also reveals something crucial about the nature of climate tipping points. The transition from the pre-Carnian arid conditions to the extreme wet conditions appears to have happened relatively quickly in geological terms. Once the atmospheric system crossed a critical threshold, it locked into a new stable state that persisted for millions of years. This kind of rapid transition between stable climate states is exactly what climate scientists worry about in our current situation. The Earth's climate system has multiple possible equilibrium states, and rapid changes in atmospheric composition can potentially push the system from one state to another with little warning. The recovery from the Carnian pluvial episode was also a gradual process that took millions of years. Even after the volcanic emissions finally decreased and the rains began to subside, it took a very long time for ecosystems to stabilize and for atmospheric composition to return to more normal levels. This suggests that once triggered, extreme climate changes can become self-sustaining for geological ages. The sheer scale of destruction during those 2 million years is almost impossible for the human mind to grasp. Picture the most devastating flood in recorded history, then multiply that by thousands and stretch it across geological time. Rivers became raging torrents that carved new channels across continents. Lakes expanded into inland seas. Coastlines were completely redrawn as sea levels fluctuated wildly. But the most haunting aspect of the Carnian pluvial episode wasn't just the relentless precipitation, it was what happened to the survivors. Archaeological evidence suggests that life didn't simply endure during this period, it was forced to completely reinvent itself. Species that had thrived for millions of years in stable ecosystems suddenly found themselves in an alien world where the very rules of survival had changed overnight. The fossil record from this time period tells a story of desperate adaptation. We find evidence of plants developing entirely new root systems capable of surviving in perpetually waterlogged soils. Animals evolved different respiratory systems to cope with the oxygen-depleted air that resulted from constant moisture. Some species developed migration patterns that would have seemed impossible before the rains began, following seasonal variations in rainfall intensity that became the only predictable aspect of their environment. What's particularly striking is how this event reveals the interconnectedness of Earth's systems. The prolonged rainfall didn't just affect terrestrial environments, it fundamentally altered ocean circulation patterns, disrupted seasonal weather cycles, and even changed the planet's albedo as vast areas of desert were replaced by swampland and forests. The Earth's energy balance shifted so dramatically that it took millions of years for natural feedback mechanisms to restore some semblance of stability. Scientists studying sediment cores from this period have discovered layers of rock that contain no evidence of dry seasons whatsoever. These geological time capsules preserve chemical signatures indicating that some regions experienced continuous saturation for hundreds of thousands of years without interruption. The implications are staggering when you consider that most modern ecosystems depend on seasonal dry periods for everything from seed germination to nutrient cycling. The atmospheric dynamics during the Carnian pluvial episode were unlike anything we observe in the modern world. Computer models attempting to recreate these conditions suggest that the planet may have experienced mega monsoons, massive storm systems that dwarfed anything in recorded history. These weren't ordinary rainstorms. They were continent-spanning weather phenomena that could drop years' worth of modern precipitation in a matter of days. The energy requirements for sustaining such extreme weather patterns over geological timescales are mind-boggling. The atmospheric system was essentially running in overdrive, powered by the enormous heat capacity of the superheated oceans and the continued volcanic emissions. It created a positive feedback loop where increased evaporation led to more precipitation, which led to further changes in atmospheric chemistry, which sustained the cycle indefinitely. Perhaps most disturbing is what happened to the regions that weren't directly affected by the volcanic emissions. Even areas thousands of miles away from the primary eruption sites experienced dramatic climate changes. The global atmospheric circulation system redistributed heat and moisture in patterns that created extreme weather conditions across the entire planet. No corner of Earth was safe from the consequences of what was happening in the Rangelia province. The marine fossil record from this time shows evidence of massive disruptions to ocean ecosystems. Coral reefs, which had been stable for millions of years, suffered near total collapse as ocean chemistry changed and sediment loads from increased erosion buried shallow marine environments. Deep ocean environments fared somewhat better, but even these were affected by changes in water temperature and chemical composition that filtered down from the surface. One of the most chilling discoveries comes from paleosol studies, investigations of ancient soil geological record. These studies' layers preserved in the reveal that in many regions, normal soil formation processes completely shut down during the Carnian pluvial episode. The constant saturation prevented the development of typical soil horizons, creating instead vast areas of waterlogged sediment that couldn't support normal plant communities. The impact on the nitrogen and carbon cycles was equally dramatic. The constant moisture accelerated chemical weathering processes, stripping nutrients from rocks at unprecedented rates while simultaneously preventing normal decomposition processes in waterlogged soils. This created a complex biogeochemical crisis that affected everything from individual plant nutrition to global atmospheric composition. But here's what makes the Carnian pluvial episode truly terrifying from a modern perspective. The rate of carbon emissions that triggered this ancient catastrophe may have been similar to what we're producing today through fossil fuel combustion and deforestation. The main difference is duration. The Carnian volcanic systems sustained their emissions for millions of years, while human activities have been ramping up for only a few centuries. This raises the deeply unsettling question of what might happen if we continue on our current trajectory. Are we inadvertently recreating the atmospheric conditions that triggered the most extreme weather event in Earth's history? The parallels are too significant to ignore, especially when we consider that modern climate models predict increasing precipitation intensity in many regions as global temperatures rise. The paleoclimatic data from the Carnian period also reveals something crucial about climate sensitivity. The Earth's climate system responded to changes in atmospheric composition much more dramatically than many current models predict. This suggests that our estimates of future climate change impacts may be overly conservative, particularly regarding precipitation patterns and extreme weather events. Recent research has uncovered evidence that the Carnian pluvial episode wasn't uniform across the globe. Different regions experienced different patterns of extreme weather, creating a complex mosaic of climatic conditions that changed the evolutionary trajectory of life on different continents. Some areas became perpetual swamplands, while others experienced alternating periods of flooding and drought that were even more destructive than continuous rain. The recovery period following this ancient catastrophe offers both hope and warning for our current situation. While life did eventually adapt and diversify after the extreme conditions ended, it took millions of years for ecosystems to fully stabilize. Many species that went extinct during the Carnian were never replaced by similar organisms, representing permanent losses to Earth's biodiversity that persisted long after conditions returned to normal. The Carnian pluvial episode fundamentally changed the trajectory of evolution on Earth. Without this catastrophic event, dinosaurs might never have risen to dominance. The mammals that eventually gave rise to humans might have followed completely different evolutionary pathways. In a very real sense, this ancient climate disaster shaped the biological world that we inherited millions of years later. Modern climate scientists studying the Carnian period have identified several key tipping points that sustained the extreme conditions for such an extended period. Once the atmospheric system crossed certain thresholds of temperature and humidity, it became locked into a new stable state that was self-reinforcing. Breaking out of this stable state required external changes that took geological ages to develop. This concept of climate system stability and tipping points is central to understanding our current climate crisis. The Earth's climate has multiple possible equilibrium states, and rapid changes in atmospheric composition can potentially trigger transitions between these states with little warning. The Carnian pluvial episode demonstrates that once such a transition occurs, returning to previous conditions is neither quick nor guaranteed. The geological evidence suggests that the end of the Carnian pluvial episode came gradually as volcanic activity decreased and natural carbon sequestration processes slowly removed excess carbon dioxide from the atmosphere. But even after the rains finally began to subside, it took millions of years for ecosystems to fully recover and for new evolutionary radiations to replace the species that had been lost. What makes the Carnian pluvial episode even more remarkable is how it reveals the hidden connections between seemingly unrelated Earth systems. As the relentless rains continued decade after decade, they began to trigger cascading effects that nobody could have predicted. The constant moisture didn't just change weather patterns. It fundamentally altered the planet's chemistry, biology, and even its geology in ways that are still being discovered today. One of the most startling revelations comes from studying ancient river systems during this period. geologists have found evidence that some of the world's major river networks were completely reorganized during the Carnian rains. Rivers that had flowed in the same direction for millions of years suddenly carved entirely new channels as the sheer volume of water overwhelmed their existing paths. We're talking about geological features that normally take tens of millions of years to form being reshaped in mere thousands of years. The implications become even more staggering when you consider what this meant for sediment transport. These supercharged river systems were moving unimaginable quantities of rock, soil, and organic matter across continents. Mountain ranges were being eroded at rates that defy modern understanding. Valleys were filled with sediment loads equivalent to entire modern mountain ranges. The very topography of Earth was being rewritten by the power of water. But perhaps the most mind-bending aspect of this ancient catastrophe was its impact on atmospheric pressure itself. Scientists analyzing tiny bubbles of ancient air trapped in amber from this period have discovered that atmospheric pressure during the Carnian may have been significantly higher than today. The massive amounts of water vapor and other gases being pumped into the atmosphere actually changed the weight of the air itself. This atmospheric thickening had profound consequences for life on Earth. Higher atmospheric pressure would have affected how organisms breathed, how their circulatory systems functioned, and even how they moved. Animals that had evolved in lower pressure conditions suddenly found themselves struggling with basic physiological processes. It was like every living thing on the planet was suddenly transported to a different world with different physical laws. The plant kingdom's response to these conditions reveals just how extreme the Carnian environment really was. Fossil evidence shows that during this period, some plant species developed root systems that extended hundreds of feet deeper than their modern relatives. These weren't gradual evolutionary adaptations developed over millions of years. These were desperate survival responses that occurred within thousands of generations as plants literally grew or died, trying to find stable ground in a world where the water table had essentially disappeared as a meaningful concept. Even reproduction during this time, many more bizarre, was what happened to plant species abandoned their normal reproductive cycles entirely, developing new strategies for spreading their genes in an environment where traditional seed dispersal mechanisms no longer worked. Some plants evolved to reproduce exclusively through fragmentation, breaking apart and regenerating from pieces that could survive being washed thousands of miles from their parent plants. The marine environment during the Carnian tells an equally extraordinary story. A soared into the oceans from massive amounts of freshwater the continents. Entire ocean basins experienced dramatic changes in the fossility. Record shows that marine organisms adapted to these changing conditions in ways that seem almost impossible. Some species that had been exclusively saltwater organisms developed the ability to survive in brackish or even freshwater conditions within relatively few generations. The deep ocean currents that regulate Earth's temperature were completely disrupted during this period. The normal thermohaline circulation patterns that moved by the massive influx of fresh heat around the planet were overwhelmed. This created temperature anomalies in ocean basins that persisted for hundreds of thousands of years. Some regions of the deep ocean became significantly warmer than the surface waters above them, creating upside-down temperature profiles that defied normal oceanographic principles. Perhaps most disturbing from a modern perspective is what happened to the planet's ice sheets during the Carnian. Even though this occurred during a generally warm period in Earth's history, there were still significant ice deposits at the poles. The extreme warming triggered by the volcanic emissions and greenhouse gas accumulation caused rapid melting of these ice sheets, contributing to sea level rises that flooded vast areas of the continents. The rate of this ice melting was extraordinary, even by geological standards. Evidence suggests that sea levels may have risen by hundreds, just a few thousand feet within years during the most intense phases of the Carnian pluvial episode. Entire continental shelves that had been dried for millions of years were suddenly submerged under hundreds of feet of water. This level rise created massive its own feedback loops that sustained the extreme conditions. As more ocean surface area was exposed to the atmosphere, evaporation rates increased even further. The newly flooded continental areas became vast seas that absorbed shallowed enormous amounts of solar energy, heating the water and pumping even more moisture into the already saturated atmosphere. The impact on terrestrial ecosystems was nothing short of apocalyptic. Fossil evidence shows that entire biomes that had existed for millions of years were completely eliminated during this period. Desert-unique ecosystems that had supported communities of drought-adapted organisms were transformed overnight into swamplands, virtually geological terms. The species that had thrived in these environments had nowhere to go and no time to adapt. But the Carnian pluvial episode also reveals something remarkable about the resilience of life itself. While many species went extinct, others underwent rapid evolutionary radiations that filled the new ecological niches created by the extreme conditions. The fossil record shows an explosion of diversity among aquatic in this period. ASD semi-aquatic organisms during life rushed to exploit the vast land habitats that new wet had suddenly appeared across the globe. Some of the most fascinating innovations evolutionary occurred among that would eventually give rise to both the early archosaurs, the group dinosaurs, and crocodilians. The extreme environmental pressures of the Carnian period appear to have accelerated their evolutionary development in ways that prepared them to dominate terrestrial ecosystems for the next 200 million years. The physiological adaptations that evolved during this period were extraordinary. Some early archosaurs developed more efficient respiratory systems that could extract oxygen from the humid, oxygen-depleted air that characterized the Carnian atmosphere. Others evolved enhanced kidneys that could process the massive water loads their bodies absorbed in the perpetually humid environment. Even more remarkable were the behavioral adaptations that emerged during this time. Fossil trackways from the Carnian period show evidence of complex migration patterns that had never existed before. Some species developed seasonal movement cycles that covered thousands of miles as they followed the subtle variations in rainfall intensity that became the only predictable aspect of their environment. The social behaviors of many species also underwent dramatic changes during the Carnian. Evidence suggests that some animals that had previously been solitary began forming large cooperative groups to better survive the harsh conditions. Fossil sites from this period show unprecedented concentrations of individuals from multiple species, suggesting that the extreme environment forced different types of animals to work together in ways that had never occurred before. The Carnian period also provides crucial insights into how ecosystems recover from extreme climate events. The fossil record shows that recovery didn't happen uniformly across the globe or across different types of organisms. Some ecosystems bounced back relatively quickly once conditions began to stabilize, while others took millions of years to develop new stable communities. Interestingly, many of the ecosystems that emerged after the Carnian were more complex and resilient than those that had existed before. The extreme environmental pressures had essentially stress-tested life on Earth, eliminating less adaptable species and promoting the evolution of organisms that could survive in highly variable conditions. This pattern of destruction followed by innovation appears to be a recurring theme in Earth's history, but the Carnian pluvial episode represents one of the most extreme examples. The sheer duration and intensity of the environmental changes created evolutionary pressures that were unprecedented in their scope and persistence. Modern genetic studies of organisms whose lineages survived the Carnian period reveal molecular signatures of this ancient catastrophe. DNA analysis shows evidence of population bottlenecks and rapid evolutionary changes that occurred during this time, providing biological confirmation of the extreme environmental pressures documented in the fossil record. The chemical signatures preserved in rocks from the Carnian period paint an even more detailed picture of the catastrophe. Isotopic analysis reveals that the planet's entire biogeochemical cycle was disrupted for millions of years. The normal cycling of carbon, nitrogen, sulfur, and other essential elements was thrown into chaos by the extreme conditions. One particularly striking piece of evidence comes from studying the ratio of different carbon isotopes in Carnian-age rocks. These ratios show massive fluctuations that indicate the planet's carbon cycle was in a state of complete instability. The volcanic emissions were pumping carbon into the atmosphere faster than natural processes could remove it, while the extreme weather was disrupting normal carbon sequestration mechanisms. The sulfur cycle was equally disrupted during this period. The massive volcanic emissions included enormous quantities of sulfur compounds that created acid rain on a scale that's difficult to imagine. This acid rain accelerated the weathering of rocks and soils, releasing additional greenhouse gases and further destabilizing the climate system. The nitrogen cycle also went haywire during the Carnian. The waterlogged soils that covered vast areas of the continents prevented normal nitrogen cycling processes. At the same time, increased lightning activity associated with the intense storm systems may have dramatically increased the rate of atmospheric nitrogen fixation. These changes in nitrogen availability had cascading effects on plant communities and the animals that depended on them. What makes these biogeochemical disruptions particularly significant is how long they persisted. Evidence suggests that some of these elemental cycles remained unstable for millions of years after the most intense phase of the Carnian pluvial episode had ended. This indicates that the damage to Earth's chemical systems was so severe that natural recovery processes were overwhelmed for geological ages. The Carnian period also provides crucial insights into the relationship between biodiversity and ecosystem stability. Before this catastrophe, many ecosystems had been relatively stable for millions of years, dominated by a few highly specialized species. But these stable, low-diversity systems proved to be extremely vulnerable to the rapid environmental changes of the Carnian. In contrast, the ecosystems that emerged after the crisis were characterized by higher diversity and more complex food webs. These more diverse systems proved to be more resilient to environmental fluctuations, suggesting that the Carnian catastrophe may have actually improved the long-term stability of life on Earth by promoting the evolution of more robust ecological communities. This relationship between diversity and stability has profound implications for understanding current biodiversity loss and climate change. If the patterns observed during the Carnian hold true, our current reduction in global biodiversity may be making Earth's ecosystems more vulnerable to the climate disruptions we're already beginning to experience. The paleontological record from the end of the Carnian pluvial episode reveals that the transition back to more normal conditions was gradual and uneven. Different regions of the globe experienced the end of the extreme conditions at different times, creating a complex mosaic of recovering and still disrupted ecosystems that persisted for millions of years. Some areas that had been completely transformed during the height of the Carnian never fully returned to their pre-catastrophe conditions. The geological and ecological changes had been so severe that entirely new types of environments persisted long after the rains had stopped. These novel ecosystems became the foundation for new evolutionary radiations that would shape life on Earth for the remainder of the Mesozoic era. The study of these ancient novel ecosystems provides important insights into how modern ecosystems might respond to current and future climate change. The Carnian period demonstrates that extreme environmental changes don't just temporarily disrupt existing systems. They can create entirely new types of environments that persist for geological ages and support completely different communities of organisms. Perhaps most sobering is what the Carnian pluvial episode reveals about the potential for rapid, irreversible changes in Earth's climate system. The transition into the extreme conditions appears to have occurred much more rapidly than the recovery. This asymmetry suggests that it's much easier to destabilize the volcanic's climate than to restore it once it's been disrupted. Emissions that triggered the Carnian catastrophe continued for millions of years, but the most dramatic environmental changes occurred during the first few 100,000 years of the crisis. This indicates that Earth's climate system has the potential to respond much more quickly to petascales required for natural recovery processes urbations than the time to restore stability. This pattern of rapid onset and slow recovery is particularly relevant to our current situation, where human activities are changing atmospheric composition at rates that are comparable to, or even faster than, the volcanic emissions that triggered the Carnian crisis. If the ancient patterns hold true, we may be approaching thresholds that could trigger rapid climate changes that would persist for geological timescales, even if we immediately stopped all greenhouse gas emissions. The Carnian pluvial episode stands as perhaps the most powerful demonstration in Earth's history of how quickly and completely our planet's climate system can change when pushed beyond certain critical thresholds. It's a sobering reminder that the stable climate conditions that have allowed human civilization to flourish are neither permanent nor guaranteed, and that the consequences of crossing certain atmospheric tipping points may be far more severe and long-lasting than we've dared to imagine. The most chilling aspect of studying the Carnian pluvial episode isn't just the scale of destruction it reveals, but how it exposes the terrifying speed at which our planet can shift into completely alien states. When scientists first began reconstructing this ancient catastrophe, they expected to find evidence of gradual change over millions of years. Instead, they discovered something far more disturbing. The transition into the most extreme phase of the Carnian appears to have occurred within just a few thousand years. In geological terms, this is essentially instantaneous. One day, Earth was a hot but relatively stable world. Within a few millennia, it had become something that would be utterly unrecognizable to any modern observer. The evidence comes from some for this rapid transition of the most precise geological dating techniques ever developed. Scientists studying rock layers from this period can literally see the moment when everything changed. Below certain sediment layers, you find fossil chemical signatures consistent with normal conditions in the Triassic. Above those fin layers, you'd evidence of a world in complete environmental precision chaos. This, in geological, the record allows us to understand just that, not the Carnian happened, but exactly how it unfolded. The story that aiding System 1 of cask failures balance. Each change triggered multiple environmental to restorated beyond any natural ability other far changes, creating feedback loops that ample beyond what the initialified the crisis volcanic emissions alone could have caused chemistry from this. The atmospheric data feedback these how disturbing about something particularly period reveals. As loops operate, temperatures so global precipitation ardent intensified vast areas of frost that of perm had been locked away for millions of years, began to deal with enormous quantities of previously sequenced thaw. This release estered carbon into the atmosphere, further accelerating the warming in a process that became completely self-sustaining. But the permafrost melting was just one of many feedback mechanisms that kicked in during the early phases of the Carnian crisis. Atmospheric moisture created more extensive. The increased cloud cover, which initially provided some cooling through increased reflection of solar radiation. However, the water vapor itself acted as a powerful greenhouse gas, trapping heat in the lower atmosphere and ultimately more warming. The ocean, contributing to even currents that normally helped regulate global temperatures, were disrupted by the massive influx of fresh water from the continents. This disruption weakened the natural heat transport mechanisms that had kept regional climates relatively stable. Areas that had previously enjoyed moderate temperatures suddenly experienced extreme conditions as the ocean's ability to moderate climate variations broke down. Perhaps most terrifying was what happened to the planet's natural carbon sequestration systems. Under normal conditions, weathering of rocks and the burial of organic matter in sediments gradually removes carbon dioxide from the atmosphere, providing a natural thermostat that prevents runaway climate change. But during the Carnian, these processes were overwhelmed by the sheer volume of carbon being released into the system. The constant rainfall accelerated chemical weathering to unprecedented rates, but instead of removing carbon from the atmosphere, it released even more greenhouse gases from rocks and soils. The waterlogged conditions prevented normal decomposition processes, but they also prevented the burial of organic carbon that would normally sequester atmospheric CO2. Every natural mechanism that might have provided stability was either overwhelmed or actively contributing to the crisis. The biological systems that normally help regulate Earth's climate were equally disrupted. Vast forests that had acted as carbon sinks were drowned by the persistent flooding. Marine ecosystems that process enormous quantities of atmospheric carbon were devastated by ocean acidification and changing salinity levels. The living components of Earth's climate system, which normally provide crucial feedback mechanisms, became part of the problem rather than the solution. What makes this ancient catastrophe particularly relevant to our current situation is how it demonstrates the concept of climate tipping points in action. Modern climate scientists worry about crossing thresholds where the climate system shifts into new stable states that are very difficult to reverse. The Carnian pluvial episode provides a perfect example of exactly this kind of transition occurring in Earth's past. The geological evidence suggests that once the Carnian climate system crossed certain critical thresholds, it became locked into the extreme state for millions of years. Even when volcanic emissions began to decrease, the climate didn't immediately return to previous conditions. The system had found a new equilibrium point that was maintained by the complex interactions between atmosphere, oceans, and biosphere that had been fundamentally altered by the initial crisis. Breaking out of this new climate state required external changes that took geological ages to develop. Gradual changes in continental positions, slow evolution of new biological communities, and the long-term effects of weathering and erosion eventually combined to shift the system back toward more moderate conditions. But this recovery process took far longer than the initial transition into crisis. This asymmetry between rapid onset and slow recovery appears to be a fundamental characteristic of Earth's climate system. It's much easier to push the planet into extreme states than to pull it back out once it's crossed certain thresholds. The implications for our current situation are deeply unsettling, especially when we consider that human activities are currently changing atmospheric composition at rates that rival or exceed the volcanic emissions that triggered the Carnian catastrophe. The study of ancient climate analogues like the Carnian period has become increasingly important as we try to understand what might happen if current trends continue. While every climate crisis is unique, the basic physics and chemistry that govern Earth's climate system remain constant across geological time. The same processes that created the Carnian nightmare could potentially operate again under the right conditions. Modern climate models incorporate many of the same feedback mechanisms that operated during the Carnian, but most current projections assume that we can avoid crossing the kinds of tipping points that led to such extreme conditions in the past. The geological record suggests this assumption may be overly optimistic. Earth's climate system has repeatedly demonstrated its capacity for rapid, dramatic changes when pushed beyond certain limits. The Carnian period also reveals something crucial about the relationship between climate stability and the complexity of life on Earth. The extreme conditions didn't just stress individual species or ecosystems, they fundamentally altered the evolutionary trajectory of life itself. The crisis eliminated entire lineages while creating opportunities for others to radiate into new ecological niches. The dinosaurs that eventually came to dominate terrestrial ecosystems might never have risen to prominence without the ecological disruptions of the Carnian period. The mammalian lineages that eventually gave rise to humans were profoundly shaped by the environmental pressures of this ancient climate crisis. In a very real sense, we are the descendants of the survivors of the most extreme weather event in Earth's history. This evolutionary dimension of the Carnian catastrophe highlights another disturbing parallel with our current situation. We're not just facing potential changes in temperature or precipitation patterns, we're potentially facing changes that could alter the entire trajectory of evolution on Earth. The species that survive whatever climate changes lie ahead may be very different from the ones that exist today. The fossil record from the Carnian period shows that survival during extreme climate events often depends more on adaptability and generalized traits than on being perfectly adapted to specific conditions. Specialists that had evolved to thrive in particular environments were often the first casualties when those environments disappeared. Generalists that could adapt to changing conditions were more likely to survive and diversify in the post-crisis world. This pattern has profound implications for conservation strategies in our current era of rapid environmental change. Protecting biodiversity may require focusing not just on preserving existing species and ecosystems, but on maintaining the genetic and ecological diversity that provides the raw material for adaptation to future conditions. The Carnian period also demonstrates how environmental changes can create novel selective pressures that drive rapid evolutionary innovation. Some of the most important evolutionary developments in vertebrate history occurred during or shortly after this ancient climate crisis. The extreme conditions essentially accelerated evolution by creating new challenges that required new solutions. The respiratory systems that allowed dinosaurs to become so successful appear to have evolved during this period of atmospheric stress. The advanced cardiovascular systems that eventually enabled the evolution of warm-blooded metabolism may have first developed as adaptations to the oxygen-depleted conditions of the Carnian atmosphere. The crisis didn't just eliminate species, it created the evolutionary innovations that would define life on Earth for the next 200 million years. But perhaps the most important lesson from the Carnian pluvial episode is how it reveals the interconnectedness of all Earth systems. The volcanic emissions that started the crisis affected not just atmospheric chemistry, but ocean circulation, soil formation, plant communities, animal behavior, and evolutionary processes. Changes in one component of the Earth system cascaded through every other component in ways that amplified and sustained the crisis. Modern Earth system science recognizes these same interconnections operating today. Changes in atmospheric composition affect not just climate, but ocean chemistry, terrestrial ecosystems, soil health, water cycles, and countless other processes. The Carnian period provides a stark example of what can happen when these interconnected systems are pushed beyond their ability to maintain stability. The recovery from the Carnian crisis was equally complex and interconnected. It wasn't just a matter of atmospheric composition returning to normal levels. New ecosystems had to evolve. New biogeochemical cycles had to establish themselves, and new relationships between different components of the Earth system had to develop. This recovery process took millions of years precisely because so many different systems had to be rebuilt from the ground up. Understanding this complexity is crucial for grappling with current climate challenges. Simple solutions that focus on just one aspect of the problem, like reducing atmospheric CO2 levels, may be insufficient if other components of the Earth system have already been destabilized. The Carnian period suggests that once certain thresholds are crossed, recovery requires coordinated changes across multiple Earth systems that can take geological timescales to accomplish. The implications become even more sobering when we consider the current rate of environmental change. The Carnian crisis unfolded over thousands to millions of years, providing at least some time for evolutionary and ecological adaptation. Current human-driven changes are happening over decades to centuries, potentially giving natural systems no time to adjust before being overwhelmed by the next wave of changes. This acceleration of environmental change may be pushing us toward a crisis that could be even more severe than the Carnian catastrophe. While the ancient volcanic emissions continued for millions of years, they started from a baseline atmosphere that was already adapted to high CO2 levels. Current emissions are pushing atmospheric composition into ranges that haven't existed since long before complex life evolved on Earth. The Carnian pluvial episode stands as both a warning and a testament to the resilience of life on Earth. It shows us that our planet can survive even the most extreme environmental catastrophes. But it also reveals the enormous costs of such survival. The Earth that emerged from the Carnian crisis was profoundly different from the one that entered it, and the changes persisted for geological ages. As we face our own potential climate crisis, the lessons from 232 million years ago become increasingly relevant. We're conducting an uncontrolled experiment with our planet's climate system, and the Carnian period provides a glimpse of just how extreme the consequences might be if we push too hard, too fast, beyond the natural limits of Earth's ability to maintain stability. The rain that fell for 2 million years straight wasn't just weather. It was a fundamental reorganization of how our planet works, triggered by changes in atmospheric composition that may have been no more dramatic than what we're causing today. The question isn't whether Earth's climate can change dramatically. The Carnian period proves it can. The question is whether we're wise enough to learn from this ancient catastrophe before we trigger our own version of the same fundamental forces that once transformed our planet into an alien world of endless rain. The evidence from the Carnian period reveals something that should make every modern human profoundly uncomfortable about our current trajectory. When paleoclimatologists first began studying this ancient catastrophe, they assumed the extreme conditions would show clear signs of gradual onset. What they found instead was evidence of a climate system that could flip like a switch from one stable state to another, with virtually no warning period. The rock record from multiple sites across the globe tells the same terrifying story. Below a certain geological layer, you find fossils and chemical signatures consistent with the hot but relatively stable conditions that had persisted for millions of years. Above that layer, everything changes. The transition zone between these two worlds is often less than a few feet thick in the rock record, representing perhaps only a few centuries of geological time. This razor-thin boundary preserves the moment when Earth's climate crossed a point of no return. Chemical analysis of these boundary layers shows massive spikes in atmospheric carbon dioxide, followed immediately by evidence of ecosystem collapse and the beginning of the endless rains. The speed of this transition challenges every assumption we have about how gradually climate systems respond to environmental pressures. But what happened next is even more disturbing. Once the planet crossed into the extreme Carnian state, it didn't just stay there temporarily until the volcanic emissions stopped. It became locked into this new configuration for millions of years, sustained by feedback mechanisms that operated independently of the original volcanic trigger. The climate system had found a new equilibrium point, and it was remarkably stable despite being utterly alien by previous standards. The atmospheric chemistry during the peak Carnian period was so radically different from anything in modern experience that it challenges our ability to comprehend what Earth was actually like during this time. Atmospheric pressure may have been 30 to 40% higher than today due to the massive amounts of water vapor and volcanic gases filling the air. The composition of the atmosphere itself was alien, with carbon dioxide levels reaching concentrations that would be lethal to most modern land animals. Oxygen levels fluctuated wildly during this period, sometimes dropping to concentrations that would cause immediate unconsciousness in modern humans, then spiking to levels that would make the air itself combustible. These fluctuations were driven by the complex interactions between massive amounts of decaying organic matter in waterlogged soils and the disrupted photosynthetic processes of stressed plant communities. The temperature gradients across Earth's surface during the Carnian were unlike anything that exists today. While global average temperatures were extreme, the distribution of heat was equally bizarre. Some regions experienced temperature differences of 50 degrees Celsius between day and night, while others maintained almost constant temperatures for months at a time. The normal patterns of heat distribution that create recognizable seasons and weather patterns had completely broken down. The hydrological cycle during this period operated according to principles that seem to violate everything we understand about how water moves through Earth's systems. Some regions received the equivalent of decades' worth of modern rainfall in single storm events. Other areas experienced precipitation that fell continuously at moderate rates for thousands of years without interruption. Still others alternated between devastating floods and complete drought in cycles that lasted centuries. The energy requirements for sustaining such extreme weather patterns reveal something profound about the hidden power of Earth's climate system. Computer models attempting to recreate Carnian conditions require atmospheric energy budgets that are almost incomprehensible. The amount of energy being cycled through evaporation, precipitation, and storm formation was equivalent to the output of thousands of major volcanic eruptions occurring simultaneously and continuously for millions of years. This energy came from the superheated oceans, which had absorbed enormous amounts of thermal energy from the enhanced greenhouse effect. But once this energy was stored in the ocean system, it created a thermal reservoir that could sustain extreme weather patterns long after the original heating had stopped. The oceans became massive batteries of atmospheric energy, capable of driving storm systems that dwarfed anything in modern experience. The biological response to these conditions reveals just how far life can be pushed before fundamental physiological limits are reached. Many organisms during the Carnian period developed adaptations that seem almost supernatural by modern standards. Some early reptiles evolved the ability to essentially shut down their metabolism for months at a time, surviving periods of extreme environmental stress by entering states of suspended animation that lasted far longer than modern hibernation. Plant communities developed survival strategies that border on the impossible. Some species evolved root systems that could function in completely waterlogged soils for decades, extracting nutrients and oxygen from environments that would kill modern plants within days. Others developed the ability to photosynthesize using different wavelengths of light, adapting to the perpetually cloudy skies that blocked most direct sunlight during the peak Carnian period. The fossil record shows evidence of plants that could literally dissolve and reconstitute themselves when environmental conditions shifted beyond their tolerance limits. These organisms would break down into component cells that could survive extreme conditions individually, then reassemble into functioning plants when conditions improved. This level of biological flexibility is almost unimaginable by modern standards. Animal behavior during the Carnian period underwent changes that seem to defy everything we know about normal ecological relationships. Predator-prey dynamics broke down as environmental stress forced species into cooperative relationships that had never existed before. Fossil trackways show evidence of mixed species herds that included animals that would normally have been competitors or enemies, united by the necessity of surviving conditions that none could endure alone. Some species developed migration patterns that covered entire continents as they followed subtle variations in the intensity of precipitation. These migrations weren't seasonal movements like modern animal migrations. They were desperate, continuous wanderings that lasted for generations as animals searched for any region where conditions might be slightly more tolerable. The social structures of many species became incredibly complex during this period, as survival required unprecedented levels of cooperation and communication. Evidence suggests that some reptilian species developed primitive language-like communication systems that allowed them to coordinate group responses to rapidly changing environmental conditions. These communication networks may have been the evolutionary foundation for the complex social behaviors that would later emerge in dinosaurs and eventually lead to intelligence in other lineages. The marine environment during the Carnian period was equally transformed, but in ways that created entirely new types of ecosystems. The massive influx of fresh water from the continents created layered ocean systems where different salinity levels supported completely different communities of organisms. Some ocean basins developed freshwater surface layers hundreds of feet thick floating above normal seawater, creating aquatic environments that had never existed before in Earth's history. These layered ocean systems supported bizarre food webs that operated according to completely novel principles. Some marine organisms evolved the ability to migrate vertically through different salinity layers to exploit different food sources at different depths. Others developed specialized organs that could function in both saltwater and freshwater conditions, allowing them to survive the constantly changing chemical composition of their environment. The deep ocean during the Carnian period became a refuge for life forms that were being devastated at the surface, but even these deep environments were profoundly affected by the global crisis. Changes in ocean circulation patterns created deep water masses with completely different temperature and chemical characteristics than anything that exists today. Some deep ocean regions became superheated by the disrupted circulation patterns, while others became colder than modern polar waters. The chemistry of seawater itself was fundamentally altered during the Carnian period. The massive amounts of volcanic emissions and weathering products being washed into the oceans created chemical conditions that were toxic to many forms of marine life. Ocean pH levels fluctuated wildly as different chemical compounds were added and removed from seawater at unprecedented rates. Some ocean basins became so acidic that they could dissolve the shells of marine organisms, while others became so alkaline that they precipitated minerals directly from seawater. These chemical changes in the oceans had cascading effects throughout the entire marine food web. Primary productivity in many ocean regions collapsed as phytoplankton communities were poisoned by the changing water chemistry. This collapse of marine primary productivity removed one of the major mechanisms for removing carbon dioxide from the atmosphere, further accelerating the atmospheric changes that were driving the crisis. But perhaps most remarkable was how marine ecosystems adapted to these impossible conditions. New types of symbiotic relationships evolved that allowed organisms to survive in waters that should have been lethal. Some marine animals developed internal chemical processing systems that could neutralize toxic compounds in their environment. Others evolved specialized feeding strategies that allowed them to exploit food sources that had been created by the environmental crisis itself. The recovery of marine ecosystems after the Carnian period took tens of millions of years and resulted in ocean communities that were fundamentally different from those that had existed before the crisis. Many of the evolutionary innovations that developed during this period of marine stress became the foundation for the great evolutionary radiations that would follow, including the diversification of marine reptiles that would dominate Mesozoic oceans. The terrestrial recovery was even more complex and prolonged. The landscapes that emerged as the endless rains finally began to subside were utterly alien compared to pre-Carnian environments. Vast areas that had been stable ecosystems for millions of years had been transformed into entirely new types of habitats that had no analogue in Earth's previous history. Some regions had been so thoroughly saturated with water for so long that they had essentially become terrestrial versions of ocean floors. These waterlogged landscapes supported communities of organisms that were neither fully terrestrial nor fully aquatic, creating transitional ecosystems that operated according to completely novel ecological principles. The soils in many regions had been so thoroughly altered by millions of years of constant saturation that they could no longer support normal plant communities even after the rains stopped. These degraded soils required millions of years of weathering and biological processing before they could sustain complex terrestrial ecosystems again. The climate patterns that emerged after the Carnian period were also fundamentally different from those that had existed before. The massive redistribution of heat and moisture during the crisis had permanently altered atmospheric and oceanic circulation patterns. New types of seasonal cycles developed that had never existed before in Earth's history, creating novel selective pressures that drove continued evolutionary change long after the crisis itself had ended. The biological communities that developed during the post-Carnian recovery period were more complex and interconnected than those that had existed before the crisis. The extreme environmental pressures had essentially forced life to develop more sophisticated strategies for dealing with environmental variability and stress. These innovations made post-Carnian ecosystems more resilient to future environmental changes, but they also made them dependent on higher levels of biological diversity and complexity. The evolutionary innovations that emerged from the Carnian crisis became the foundation for virtually every major advance in the complexity of life that would follow. The enhanced respiratory systems that allowed dinosaurs to become so successful, the complex social behaviors that would eventually lead to intelligence, and the sophisticated physiological adaptations that enabled the evolution of warm-blooded metabolism all trace their origins to the environmental pressures of this ancient catastrophe. But perhaps the most important legacy of the Carnian pluvial episode is what it reveals about the potential for rapid, fundamental changes in Earth's environment. The crisis demonstrated that our planet's climate system can shift between radically different stable states much more quickly than we previously imagined possible. Once these transitions occur, the new states can persist for millions of years, even after the original triggers have been removed. This understanding has profound implications for how we think about current environmental changes. We may be approaching tipping points that could trigger rapid transitions to climate states that would be sustained for geological timescales. The Carnian period shows us that such transitions are not just possible, but have actually occurred in Earth's past under conditions that may be similar to what we're creating today. The rate at which we're currently changing atmospheric composition rivals or exceeds the volcanic emissions that triggered the Carnian catastrophe. The main difference is that we're compressing these changes into decades rather than millennia, potentially giving Earth's systems even less time to adjust before being overwhelmed by the cascading effects of rapid environmental change. The Carnian pluvial episode stands as the most extreme example in Earth's history of what can happen when atmospheric composition is pushed beyond certain critical thresholds. It's a glimpse into a version of our planet that operated according to completely different rules, sustained by feedback mechanisms that created conditions so extreme they seem almost mythological. Yet this wasn't mythology. This was reality, preserved in stone and written in the chemical signatures of rocks that formed during those 2 million years of endless rain. The Earth that experienced this catastrophe is the same Earth we live on today, operating according to the same physical and chemical laws that governed the climate system 232 million years ago. The Carnian period forces us to confront the possibility that the stable, predictable climate that has allowed human civilization to flourish is neither permanent nor guaranteed. Our planet has repeatedly demonstrated its capacity for rapid, dramatic changes when atmospheric composition is altered beyond certain limits. We may be approaching those same limits today, conducting an uncontrolled experiment with forces that once transformed our world into an alien landscape of perpetual storms and endless rain. The terrifying reality about our current situation becomes clear when you examine the precise timing of what we're doing to our atmosphere right now. Every year, human activities pump approximately 36 billion tons of carbon dioxide into the air. That might sound manageable compared to the geological forces that triggered the Carnian catastrophe, but here's the problem. We're achieving in decades what the volcanic systems took millennia to accomplish. The Rangelia volcanic province released massive amounts of greenhouse gases, but those emissions would across Sprea thousands of years. We're compressing similar atmospheric changes into the span of a human lifetime. This acceleration means we may be approaching the same tipping points that triggered the ancient catastrophe, but with far less time for Earth's systems to adjust or adapt. Modern climate scientists have identified several critical thresholds in atmospheric carbon dioxide concentration that could trigger rapid changes in global climate patterns. Current levels have already exceeded 420 parts per million, higher than they've been for over 3 million years. The geological record from the Carnian period suggests that the most dramatic climate changes occurred when atmospheric CO2 reached concentrations between 1,500 and 2,000 parts per million. At our current rate of emissions, we could reach those dangerous levels within the next century. But the most disturbing aspect isn't just the concentration levels themselves, it's the rate of change. Earth's climate system may not be able to maintain stability when atmospheric composition changes as rapidly as we're currently causing it to change. The feedback mechanisms that operated during the Carnian period are already beginning to activate in our modern world. Arctic permafrost, which has been frozen for thousands of years, is now thawing at accelerating rates. As it melts, it releases methane and carbon dioxide that have been locked away since the last ice age. This creates exactly the kind of self-reinforcing cycle that sustained the extreme conditions during the ancient catastrophe. Ocean temperatures are rising at rates that are unprecedented in human experience, but may be similar to what occurred during the early phases of the Carnian crisis. Warmer oceans can hold less dissolved carbon dioxide, meaning they begin releasing stored CO2 back into the atmosphere. They also evaporate more rapidly, loading the atmosphere with water vapor that acts as an additional greenhouse gas. The Amazon rainforest, often lungs of the Earth, is already called the showing signs of transitioning from a carbon sink to a carbon source. During normal conditions, these forests absorb enormous quantities of CO2 from the atmosphere. But as temperatures rise and rainfall patterns change, large sections are beginning to release more carbon than they absorb. This represents another feedback loop that could accelerate atmospheric changes beyond our ability to control them. Ice sheets in Greenland and Antarctica are melting at rates that have shocked climate scientists. The most recent measurements show ice loss accelerating exponentially rather than following the gradual patterns that previous models had predicted. This rapid ice melting contributes to sea level rise, but it also affects ocean circulation patterns in ways that could trigger more widespread climate disruptions. The collapse of major ice sheets during the Carnian period contributed to sea level rises that flooded vast areas of the continents. Current ice sheet loss, while still much smaller in absolute terms, is occurring much more rapidly than the ancient melting. If current trends continue, we could see sea level changes within decades that took thousands of years to occur during the Carnian crisis. Weather patterns around the world are already becoming more extreme and unpredictable, showing signs that the atmospheric system is being pushed toward instability. Heat domes that park over regions for weeks at a time, atmospheric rivers that dump months' worth of rain in single events, and polar vortex disruptions that bring Arctic conditions to temperate zones all suggest that normal weather patterns are breaking down. These extreme weather events aren't just isolated incidents. They represent signs that the atmospheric circulation patterns that create predictable seasonal cycles are being disrupted by the rapid changes in global temperature distribution. The jet streams that normally create orderly weather patterns are becoming increasingly erratic as the temperature difference between polar and equatorial regions changes. The hydrological cycle is intensifying in ways that mirror what happened during the early stages of the Carnian period. A warmer atmosphere can hold exponentially more moisture, leading to more intense precipitation events when that moisture is finally released. Some regions are experiencing flooding events that exceed anything in recorded history, while others face droughts that persist for years longer than traditional patterns would suggest. Agricultural systems around the world are already struggling to adapt to these changing precipitation patterns. Crops that have been cultivated successfully for thousands of years are failing as rainfall timing shifts and extreme weather events become more frequent. The stability of global food production, which depends on predictable seasonal cycles, is being undermined by the increasingly chaotic behavior of weather systems. Urban areas, which house more than half of humanity, are particularly vulnerable to the kinds of extreme precipitation that characterized the Carnian period. Modern cities were designed assuming historical weather patterns would continue indefinitely. Infrastructure systems for managing stormwater, sewage, and flooding are being overwhelmed by precipitation events that exceed their design specifications. The economic costs of extreme weather are already escalating exponentially. Insurance companies are withdrawing from regions that face increasing risks of flooding, wildfires, and severe storms. The financial systems that support modern civilization assume that natural disasters will remain relatively rare and manageable. This assumption is being challenged by weather patterns that are becoming increasingly unpredictable and severe. Coastal cities around the prospect of the world face flooding as sea levels rise and storm surges become more intense. The infrastructure investments required to protect these population centers from rising waters exceed the economic capacity of many nations. Some communities are already beginning planned retreats from coastlines that may become uninhabitable within decades. The migration pressures created by changing climate conditions are beginning to strain political systems around the world. Regions that become uninhabitable due to extreme heat, flooding, or drought produce refugees who must relocate to areas that may already be struggling with their own environmental challenges. These climate-driven migrations could destabilize entire regions as populations shift in response to changing environmental conditions. Agricultural zones that have supported civilizations for millennia may become unsuitable for farming as temperature and precipitation patterns shift beyond the tolerance ranges of traditional crops. The breadbasket regions that currently feed much of the world's population could face conditions that make large-scale agriculture impossible, forcing dramatic changes in global food production and distribution systems. Water resources that have sustained human settlements for thousands of years are being disrupted by changing precipitation patterns and increasing evaporation rates. Aquifers that took millennia to fill are being drained faster than they can be replenished, while surface water sources become unreliable as weather patterns become more erratic. The energy systems that power modern civilization are increasingly vulnerable to extreme weather events. Power grids designed for historical climate conditions are being overwhelmed by heat waves that increase demand while simultaneously reducing the efficiency of generation and transmission systems. Renewable energy systems that depend on predictable wind and solar patterns face challenges as weather becomes more chaotic. Transportation networks that connect the global economy are being disrupted by extreme weather events with increasing frequency. Airports close due to unprecedented heat that affects aircraft performance. Railways buckle under temperature extremes they weren't designed to handle. Shipping routes face disruption from storms that exceed historical norms and sea level changes that affect port operations. The biological systems that support human life are showing signs of stress that echo the ecosystem collapses documented during the Carnian period. Pollinator populations are declining as flowering seasons shift and extreme weather disrupts reproductive cycles. Ocean ecosystems are being acidified by absorbed CO2, while warming waters create dead zones where marine life cannot survive. Forest ecosystems around the world are experiencing mortality events that suggest they're being pushed beyond their adaptive limits. Entire forests are dying as temperatures exceed their tolerance ranges and precipitation patterns shift beyond their evolutionary experience. These forest deaths release stored carbon back into the atmosphere while eliminating crucial carbon sinks that help stabilize climate. Coral reef systems, which support enormous marine biodiversity and protect coastlines from storm damage, are experiencing bleaching events that are becoming more frequent and severe. Ocean temperatures that exceed coral tolerance limits for extended periods cause these ecosystems to collapse, eliminating habitat for countless marine species while reducing the ocean's capacity to absorb atmospheric carbon. The Arctic region, which plays a crucial role in regulating global climate patterns, is warming at rates that are double the global average. The loss of reflective ice surfaces means more solar energy is absorbed by dark ocean water, accelerating the warming process. This Arctic amplification effect could trigger rapid changes in global atmospheric circulation patterns. Permafrost regions that have remained frozen for thousands of years are thawing at accelerating rates, releasing methane and carbon dioxide that have been stored since the last ice age. Some estimates suggest that permafrost contains more stored carbon than currently exists in the entire atmosphere. The release of even a fraction of this carbon could trigger runaway warming that exceeds our ability to control through emissions reductions. The speed of these changes is what makes our current situation potentially more dangerous than the Carnian catastrophe. While the ancient volcanic emissions continued for millions of years, they began atmospheric conditions that had been relatively stable for geological ages. We're starting from a much more precarious position and pushing the system much harder and faster than the geological processes that triggered the ancient crisis. Modern computer models that attempt to project future climate conditions are based on assumptions about how Earth's systems respond to changing atmospheric composition. These models incorporate many of the same feedback mechanisms that operated during the Carnian period, but they may not fully account for the potential for rapid, non-linear changes when multiple systems reach tipping points simultaneously. The Carnian period demonstrates that Earth's climate system can remain stable for millions of years, then suddenly shift to a completely different state within a few thousand years. Once such transitions occur, returning to previous conditions requires changes that take geological timescales to develop. We may be approaching similar transition points today, but with far less time to adapt to whatever new climate state might emerge. The question isn't whether Earth's climate can change dramatically. The geological record proves it can and has done so repeatedly throughout our planet's history. The question is whether human civilization can survive the kinds of rapid, extreme changes that have occurred in the past when atmospheric composition was altered as quickly as we're currently altering it. The Carnian pluvial episode offers both a warning and a preview of what might happen if we continue on our current trajectory. 2 million years of continuous rain may sound like ancient history, but the same physical and chemical processes that created those impossible conditions are operating in our atmosphere today. The only difference is the timescale, and that difference might make our situation even more dangerous than the ancient catastrophe that once transformed our planet into an alien world of endless storms. We're conducting an unprecedented experiment with the only planet we have, pushing atmospheric composition toward levels that haven't existed since complex life evolved on Earth. The Carnian period shows us exactly what can happen when those experiments go wrong. The rain that fell for 2 million years straight wasn't just weather. It was a fundamental breakdown of the climate systems that make our world habitable, triggered by changes in atmospheric composition that may have been no more dramatic than what we're causing now. The choice we face today is whether we'll learn from this ancient catastrophe before triggering our own version of the same fundamental forces that once turned Earth into a planet where the sun never shone and the rain never stopped. The geological record offers us a glimpse of what lies ahead if we choose poorly. The question is whether we're wise enough to heed the warnings written in stone from 232 million years ago, or whether we'll discover firsthand what it means to live on a planet where the weather itself becomes an existential threat to every living thing. The implications of what we're witnessing today become even more chilling when you examine the precise mechanisms that sustained the Carnian catastrophe for such an impossibly long duration. Scientists studying this ancient nightmare have discovered that once the extreme conditions were established, they became self-perpetuating through a series of interconnected systems that fed off each other in an endless cycle of atmospheric chaos. The key to understanding how rain could continue for 2 million years lies in recognizing that the Carnian wasn't just experiencing bad weather. It was operating under completely different atmospheric physics than anything we observe in the modern world. The sheer volume of water vapor in the air had fundamentally altered how energy moved through the climate system, creating circulation patterns that had no equivalent in Earth's previous history. During normal conditions, the atmosphere processes moisture in predictable cycles. Water evaporates from oceans and lakes, forms clouds, falls as precipitation, and returns to water bodies through rivers and groundwater. This cycle is self-regulating because the amount of moisture the atmosphere can hold is limited by temperature and pressure. But during the Carnian period, these normal limits had been completely overwhelmed. The superheated oceans were pumping water vapor into the atmosphere faster than any natural process could remove it. At the same time, the elevated atmospheric pressure meant the air could hold vastly more moisture than normal conditions would allow. This created a positive feedback loop where more evaporation led to more atmospheric moisture, which led to higher humidity levels, which reduced the atmosphere's ability to radiate heat back to space, which kept the oceans superheated and evaporating even more rapidly. But the most disturbing aspect of this cycle was how it became immune to normal regulatory mechanisms. Under typical conditions, increased cloud cover would eventually reflect enough sunlight back to space to cool the planet and reduce evaporation rates. During the Carnian, the greenhouse effect from water vapor and carbon dioxide was so intense that even with near-complete cloud cover, surface temperatures continued to climb. The atmospheric dynamics during this period created storm systems that operated according to principles we can barely comprehend today. Computer models attempting to recreate Carnian weather patterns reveal storm cells that could span entire continents, with internal energy levels equivalent to multiple Category 5 hurricanes operating simultaneously for thousands of years. These weren't individual storms in any sense we understand them. They were permanent features of atmospheric circulation, like vast weather machines that never shut down. The precipitation from these megastorms wasn't distributed randomly across the landscape. The geological record reveals highly organized patterns of rainfall that suggest the atmospheric system had developed stable circulation cells that directed moisture to specific regions with mathematical precision. Some areas received the equivalent of modern annual rainfall every few days for millennia, while nearby regions experienced different but equally extreme precipitation patterns. These organized precipitation patterns created landscapes that were unlike anything that exists on Earth today. Vast river systems developed that carried water volumes comparable to all modern rivers combined. These super rivers carved canyons and valleys in geological timescales that should have required millions of years, reshaping entire continental surfaces within thousands of years. The erosional power of these water systems was so extreme that they essentially recycled the surface of the planet during the Carnian period. Mountain ranges that had stood for hundreds of millions of years were worn down to their roots and deposited as sediment layers thousands of feet thick in what had previously been stable basins. The very topography of Earth was being rewritten by the power of moving water. But perhaps most remarkably, this massive redistribution of rock and sediment created its own feedback effects that sustained the extreme conditions. As mountains were eroded away, the exposure of fresh rock surfaces accelerated chemical weathering processes that released additional greenhouse gases into the atmosphere. The massive sediment loads being deposited in ocean basins displaced seawater and contributed to sea level fluctuations that further destabilized coastal and marine environments. The biological response to these conditions reveals just how far life can adapt when faced with seemingly impossible environmental pressures. The fossil record from the Carnian period contains evidence of evolutionary innovations that seem to defy everything we know about biological limits. Some organisms developed the ability to extract oxygen directly from water through specialized organs, allowing them to survive in air that was too humid and oxygen depleted for normal respiration. Plant communities underwent even more dramatic adaptations. Some species evolved root systems that could function as primitive gills, extracting dissolved oxygen from waterlogged soils. Others developed specialized tissues that could store months' worth of nutrients and energy, allowing them to survive extended periods when photosynthesis was impossible due to the perpetually cloudy skies. The animal kingdom's response was equally extraordinary. Some early reptiles developed primitive echolocation systems that allowed them to navigate in the perpetual twilight created by the dense cloud cover. Others evolved enhanced chemical sensing abilities that could detect food sources and safe shelter in environments where normal visual and auditory cues were useless. Perhaps most remarkably, many species developed collaborative survival strategies that had never existed before in Earth's history. Fossil evidence suggests that during the most extreme phases of the Carnian period, traditional predator-prey relationships broke down entirely. Instead, mixed communities of species worked together to survive conditions that would have been lethal to any individual organism. These collaborative communities operated according to principles that modern ecology struggles to explain. Different species would specialize in different survival functions, sharing resources and information in ways that allowed the entire community to persist in environments where individual species would have quickly gone extinct. Some communities developed rotating activity patterns where different species would be active during different phases of the endless storms, ensuring that essential functions like food gathering and shelter maintenance continued around the clock. The marine environment during the Carnian period supported equally bizarre collaborative networks. Ocean ecosystems developed multi-species associations where different organisms would specialize in processing different aspects of the radically altered ocean chemistry. Some species evolved to neutralize acidic conditions, others to process excess nutrients from terrestrial runoff, and still others to maintain oxygen levels in waters that were being depleted by massive amounts of decomposing organic matter. These marine collaborations created underwater ecosystems that functioned more like single superorganisms than traditional food webs. Different species performed specialized functions that supported the survival of the entire community, creating biological systems that were far more complex and integrated than anything that exists in modern oceans. The deep ocean environments that developed during the Carnian period were particularly alien by modern standards. The disrupted surface conditions created deep water masses with temperature and chemical characteristics that had never existed before in Earth's history. Some deep ocean regions became superheated by the chaotic circulation patterns, reaching temperatures that should have been lethal to all known forms of life. Yet even these extreme deep ocean environments supported thriving biological communities. Organisms evolved that could survive in water temperatures approaching the boiling point, developing specialized proteins and cellular structures that remained functional under conditions that would instantly kill modern marine life. These heat-adapté-made communities have been the most extreme forms of life that ever existed on Earth. The chemical processing capabilities of these deep ocean communities were equally extraordinary. They developed the ability to extract energy from chemical reactions that involved the exotic compounds being produced by the disrupted ocean chemistry. Some organisms evolved to feed directly on dissolved metals and minerals that were being concentrated in the deep waters by the chaotic circulation patterns. The recovery from the Carnian period required the complete reconstruction of Earth's biological systems from the ground up. The organisms that survived the crisis had evolved so far from their pre-Carnian ancestors that they were essentially alien life forms by previous standards. The ecosystems that emerged after the crisis were based on entirely new principles of biological organization that had been forged in the crucible of the most extreme environmental conditions in Earth's history. This biological reconstruction took millions of years and resulted in life forms that were far more complex and adaptable than those that had existed before the crisis. The evolutionary innovations that developed during the Carnian period became the foundation for every major advance in biological complexity that would follow, from the rise of dinosaurs to the eventual evolution of intelligence itself. The atmospheric recovery from the Carnian catastrophe was equally slow and complex. Even after volcanic emissions began to decrease and the most extreme weather patterns started to subside, it took millions of years for atmospheric composition to stabilize at levels that could support normal weather patterns. The feedback mechanisms that had sustained the crisis continued operating long after the original triggers had been removed. The gradual return to more normal conditions wasn't a simple reversal of the processes that had created the crisis. Instead, it required the development of entirely new atmospheric circulation patterns that could function with the altered geography and ocean chemistry that had resulted from millions of years of extreme conditions. The atmosphere essentially had to learn how to operate again under the changed physical conditions of the post-Carnian Earth. The climate system that eventually emerged from this recovery period was fundamentally different from the one that had existed before the crisis. New types of seasonal patterns developed that had never existed before in Earth's history. Weather systems operated according to different principles, creating novel environmental conditions that drove continued evolutionary innovation for millions of years after the crisis itself had ended. The ocean circulation patterns that developed during the post-Carnian recovery period were equally novel. The massive changes in ocean basin geometry and chemistry that had occurred during the crisis required the development of new circulation systems that could function under the altered physical conditions. These new circulation patterns created marine environments that had never existed before, supporting biological communities that were unlike anything in Earth's previous history. The terrestrial landscapes that emerged after the Carnian period were equally transformed. The massive erosion and sedimentation that had occurred during the crisis had created entirely new types of geological formations and soil systems. These novel landscapes supported plant and animal communities that were adapted to environmental conditions that had never existed before the crisis. The biological diversity that emerged during the post-Carnian recovery period was higher than anything that had existed before the crisis. The extreme environmental pressures had essentially forced life to develop more sophisticated strategies for dealing with environmental variability and change. This increased biological sophistication made post-Carnian ecosystems more resilient to future environmental disruptions, but it also made them dependent on higher levels of complexity and interconnectedness. The legacy of the Carnian pluvial episode can be seen in every aspect of modern Earth systems. The atmospheric circulation patterns that create our current weather systems are descended from the novel circulation patterns that developed during the post-Carnian recovery. The ocean currents that regulate our climate evolved from the circulation systems that emerged after the ancient crisis. Even the biological communities that we see today trace their fundamental organizational principles back to the collaborative survival strategies that evolved during those 2 million years of endless rain. But perhaps the most important legacy of the Carnian period is what it reveals about the potential for rapid, fundamental changes in Earth's environment. The crisis demonstrated that our planet systems can shift between radically different stable states much more quickly than we previously thought possible. Once these transitions occur, the new states can persist for millions of years, sustained by feedback mechanisms that operate independently of the original triggers. This understanding has profound implications for our current environmental situation. We may be approaching tipping points that could trigger transitions to climate states that would persist for geological timescales. The rate at which we're currently changing atmospheric composition may be pushing Earth's systems toward thresholds that could trigger rapid changes comparable to those that initiated the Carnian catastrophe. The difference is that we're compressing these changes into decades rather than millennia, potentially giving Earth's systems even less time to adjust before being overwhelmed by cascading feedback effects. The Carnian period shows us that such rapid transitions are not only possible, but have actually occurred when atmospheric composition was altered at rates comparable to what we're causing today. The question we face is whether we're wise enough to recognize the warning signs before we cross thresholds that could trigger our own version of the atmospheric chaos that once transformed Earth into a planet of endless storms. The geological record offers us a glimpse of what lies ahead if we continue on our current trajectory, but it also shows us that our planet has the capacity to recover from even the most extreme environmental catastrophes, albeit on timescales that dwarf human civilization. The choice is ours, but the window for making that choice may be closing faster than we realize. The same forces that once created 2 million years of continuous rain are stirring again in our atmosphere, and the question is whether we'll learn from this ancient catastrophe before triggering our own version of the most extreme weather event in Earth's history. The reality of our situation becomes even more terrifying when you realize that we're not just recreating the conditions that triggered the Carnian catastrophe. We're creating something potentially far worse. The ancient volcanic systems that initiated that crisis operated over geological timescales, giving Earth systems at least some time to respond and adapt. We're achieving similar atmospheric changes in a fraction of the time, compressing millions of years of geological change into mere decades. Current atmospheric carbon dioxide levels are rising at rates that are unprecedented in the geological record. Even during the most intense phases of Carnian volcanism, atmospheric composition changed more gradually than what we're experiencing today. We're essentially conducting a real-time experiment to see what happens when you push Earth's climate system harder and faster than it has ever been pushed before. The feedback mechanisms that sustained the Carnian crisis for millions of years are already beginning to activate in our modern world, but they're operating at speeds that dwarf anything in the ancient record. Arctic sea ice is disappearing at rates that have shocked climate scientists. Each summer brings new records for ice loss, exposing vast areas of dark ocean water that absorb solar heat instead of reflecting it back to space. This Arctic amplification effect is creating temperature gradients between polar and equatorial regions that are disrupting atmospheric circulation patterns in ways that mirror the early stages of the Carnian atmospheric breakdown. The jet stream, which normally creates orderly weather patterns by separating cold polar air from warm tropical air, is becoming increasingly unstable and unpredictable. Weather systems that should move predictably across continents are instead parking over regions for weeks at a time, creating prolonged heat waves, droughts, and flooding events that exceed anything in recorded history. These atmospheric river events and heat dome phenomena represent early signs that normal weather patterns are breaking down under the stress of rapidly changing temperature distributions. The hydrological cycle is intensifying in ways that directly parallel what happened during the onset of the Carnian period. Warmer air can hold exponentially more moisture, leading to precipitation events that dump months' worth of rain in single storms. Some regions are experiencing flooding that exceeds 1,000-year flood levels multiple times per decade, while others face droughts that persist for years beyond anything in historical experience. Agricultural systems around the world are struggling to adapt to these changing precipitation patterns and temperature extremes. Crops that have been cultivated successfully for millennia are failing as growing seasons shift and extreme weather becomes more frequent. The stable climate conditions that allowed human civilization to develop agriculture and permanent settlements are disappearing faster than we can adapt our systems to cope with the changes. Urban infrastructure designed for historical climate patterns is being overwhelmed by weather events that exceed design specifications. cities around the world face increasing risks of catastrophic flooding as stormwater systems designed for normal precipitation patterns are overwhelmed by the intense rainfall events that are becoming increasingly common. Coastal cities face the additional threat of rising sea levels and intensifying storm surges that could make large areas uninhabitable within decades. The ice sheets of Greenland and Antarctica are losing mass at accelerating rates, contributing to sea level rise that could eventually flood coastal areas where hundreds of millions of people currently live. The economic costs of these climate impacts are already escalating beyond what many societies can afford to manage. Insurance companies are withdrawing from regions that face increasing risks of extreme weather. Infrastructure repair and replacement costs are consuming ever larger portions of government budgets as extreme events become more frequent and severe. Agricultural productivity is declining in many regions due to heat stress, changing precipitation patterns, and increasing frequency of extreme weather events during critical growing seasons. Food security, which has been taken for granted in much decades of the world is becoming increasingly uncertain as climate conditions shift beyond the ranges that support traditional farming practices. Water resources that have sustained human settlements for thousands of years are being disrupted by changing precipitation patterns and increasing evaporation rates. Aquifers that took millennia to fill are being depleted faster than they can be recharged, while surface water sources become unreliable as weather patterns become more erratic and extreme. Energy systems designed for historical climate conditions are facing increasing stress from temperature extremes that reduce efficiency while simultaneously increasing demand. Power grids are experiencing more frequent failures as extreme heat reduces transmission capacity, while air conditioning demand reaches record levels during increasingly intense heat waves. The biological systems that support human life are showing signs of stress that echo the ecosystem collapses documented in the Carnian fossil record. Pollinator populations are declining as flowering seasons shift and extreme weather disrupts reproductive cycles. Forest ecosystems are experiencing mortality events as temperatures and drought stress exceed the tolerance ranges of tree species. Ocean ecosystems are being transformed by warming temperatures and acidification from absorbed carbon dioxide. Coral reef systems that support enormous marine biodiversity are experiencing bleaching events that are becoming more frequent and severe. Marine food webs are being disrupted as species distributions shift in response to changing ocean conditions. The speed of these changes is what makes our current situation potentially more dangerous than anything in the geological record. Evolution and natural adaptation processes that normally help ecosystems adjust to changing conditions operate over thousands or millions of years. Current climate changes are happening over decades, giving natural systems no time to adapt through normal evolutionary processes. We're witnessing the beginning of what could become the most rapid and severe climate transition in Earth's history. The same physical and chemical processes that created the Carnian nightmare are operating in our atmosphere today, but compressed into timescales that make adaptation nearly impossible for both natural systems and human societies. The geological record shows us that Earth's climate system has multiple stable states, and that transitions between these states can occur much more rapidly than the gradual changes we're accustomed to thinking about. The Carnian period demonstrates that once certain atmospheric thresholds are crossed, the climate system can lock into new configurations that persist for millions of years. Current atmospheric carbon dioxide levels are approaching concentrations that haven't existed for millions of years. We're entering atmospheric territory that complex life on Earth has never experienced. The climate conditions that emerge from this unprecedented atmospheric experiment could be unlike anything in the geological record. Computer models attempting to project future climate conditions are based on historical data and known physical relationships, but they may not capture the potential for rapid, non-linear changes when multiple Earth systems reach tipping points simultaneously. The Carnian period shows us that climate transitions can occur much more rapidly than gradual models would suggest. Ice sheet dynamics in Greenland and Antarctica are showing signs of accelerating collapse that could contribute to sea level rises measured in feet rather than inches within the coming decades. Ocean circulation patterns that regulate global temperature distribution are showing signs of instability that could trigger rapid reorganization of climate zones around the world. Permafrost regions that have remained frozen for thousands of years are thawing at unprecedented rates, releasing greenhouse gases that were stored during previous ice ages. This permafrost feedback represents a time bomb of stored carbon that could accelerate warming beyond our ability to control through emissions reductions alone. Forest systems around the world are approaching temperature and moisture thresholds beyond which they transition from carbon sinks to carbon sources. The Amazon rainforest, which has helped stabilize global climate for millions of years, is showing signs of approaching a tipping point where large areas could transition from forest to savanna within decades. These interconnected feedback systems represent the same kinds of cascading changes that transformed Earth's climate during the Carnian period. The difference is that we're triggering these changes much more rapidly than the geological processes that initiated the ancient catastrophe, potentially giving Earth's systems no time to stabilize before being pushed beyond additional tipping points. The question we face isn't whether Earth's climate can change dramatically. The geological record proves it can and has done so repeatedly. The question is whether human civilization can survive the kinds of rapid, extreme changes that occur when atmospheric composition is altered as quickly as we're currently changing it. Modern societies depend on stable, predictable climate conditions in ways that no previous civilization has experienced. Our agricultural systems, urban infrastructure, economic networks, and political institutions all assume that climate conditions will remain within historical ranges. This assumption is being challenged by changes that could push Earth's climate system into configurations that have no precedent in human experience. The Carnian pluvial episode offers both a warning and a preview of what happens when atmospheric composition is pushed beyond critical thresholds. The 2 million years of continuous rain weren't just extreme weather, they represented a fundamental breakdown of the climate systems that make our world habitable, triggered by changes in atmospheric chemistry that may have been no more dramatic than what we're causing today. We stand at a crossroads where the choices we make in the coming decades will determine whether human civilization faces a future of manageable climate changes or catastrophic disruptions that could persist for geological timescales. The geological record offers us a glimpse of both the dangers we face and the potential for recovery, but it also shows us that the costs of triggering such extreme changes are measured not in years or decades, but in millions of years of altered planetary conditions. The rain that fell for 2 million years straight stands as the ultimate demonstration of what happens when Earth's climate system is pushed beyond its breaking point. We have the knowledge to avoid repeating this ancient catastrophe, but only if we act quickly enough to prevent crossing the atmospheric thresholds that could trigger our own version of the most extreme weather event in our planet's history. The choice is ours, but the window for making that choice is closing rapidly. The same forces that once transformed Earth into an alien world of endless storms are building in our atmosphere today. The question that will define the future of human civilization is whether we're wise enough to heed the warnings written in stone from 232 million years ago, or whether we'll discover firsthand what it means to live through our own version of the catastrophe that once made rain fall continuously for 2 million years. The evidence is overwhelming, the parallels are undeniable, and the timeline for action is shrinking faster than we ever imagined possible. The Carnian pluvial episode isn't just ancient, it's a preview history of what we might be creating for ourselves if we continue down our current path of atmospheric manipulation without understanding the full consequences of the forces we're unleashing. Earth has shown us what it's capable of when atmospheric composition crosses certain critical thresholds. The question now is whether we'll learn from this ultimate climate catastrophe before we trigger our own version of the conditions that once turned our planet into a world where the sun disappeared and the rain never stopped falling. The most haunting aspect of our current trajectory becomes clear when you examine the precise speed at which we're approaching the same atmospheric thresholds that triggered the ancient catastrophe. Every measurement, every data point, every climate indicator is telling the same story. We're not just heading toward a climate crisis, we're accelerating toward it at rates that make the Carnian volcanic emissions look gradual by comparison. The mathematics are unforgiving. Current carbon dioxide emissions are injecting greenhouse gases into our atmosphere at rates that compress millions of years of geological change into mere decades. The volcanic systems that triggered the Carnian catastrophe released massive amounts of CO2, but they did so over thousands of years. We're achieving similar atmospheric changes within single human lifetimes. This compression of timescales creates a fundamental problem that no previous climate crisis has faced. Natural systems that normally provide stability and feedback regulation operate on geological timescales. They evolved to respond to changes that occur over thousands or millions of years. When you compress those same changes into decades, these regulatory mechanisms become completely overwhelmed before they can even begin to respond. The permafrost feedback loop that's currently activating across Arctic regions represents exactly this kind of overwhelmed natural system. Under normal conditions, permafrost acts as a massive carbon storage system, keeping billions of tons of greenhouse gases locked away in frozen soil. But as temperatures rise, this frozen carbon begins to thaw and release methane and CO2 into the atmosphere. The terrifying aspect of permafrost feedback isn't just the quantity of stored carbon it contains, it's the speed at which it can be released once the thawing process begins. Recent measurements from Arctic research stations show permafrost releasing greenhouse gases at rates that exceed the most pessimistic projections from just a few years ago. Some monitoring sites are detecting methane emissions that are increasing exponentially rather than following the gradual curves that climate models had predicted. This exponential acceleration is precisely the kind of non-linear response that characterized the onset of the Carnian crisis. Small changes in atmospheric composition trigger larger changes in natural systems, which release more greenhouse gases, which accelerate the atmospheric changes, creating feedback loops that become self-sustaining and impossible to control through human intervention. The Amazon rainforest represents another critical system that's approaching a tipping point where it could transition from climate stabilizer to climate accelerator. For millions of years, the Amazon has acted as one of Earth's primary carbon sinks, absorbing enormous quantities of CO2 from the atmosphere and storing it in biomass and soil. But recent studies show that large sections of the Amazon are already transitioning from carbon sinks to carbon sources. This transition isn't happening gradually over centuries as previous models suggested. Satellite data shows that the rate of Amazon forest loss and degradation is accelerating dramatically. Areas that were thriving tropical forests just decades ago are now releasing more carbon than they absorb. Drought stress, increased temperatures, and human activities are pushing this critical ecosystem beyond its ability to maintain the stable conditions it has provided for millions of years. The loss of the Amazon's climate regulation function represents a global catastrophe that extends far beyond Brazil or even South America. The Amazon rainforest generates its own weather patterns that influence global atmospheric circulation. Its massive evapotranspiration creates atmospheric rivers that carry moisture around the world. When this system breaks down, the effects cascade through global weather patterns in ways that are still being discovered. Ocean circulation systems that regulate global temperature distribution are showing similar signs of approaching critical thresholds. The Atlantic meridional overturning circulation, which includes the Gulf Stream, has been weakening at rates that suggest it could collapse within decades rather than centuries. This circulation system is responsible for keeping Europe warm and regulating weather patterns across the North Atlantic region. The collapse of major ocean circulation systems during the Carnian period contributed to the chaotic weather patterns that sustained the extreme precipitation for millions of years. Current measurements suggest we could be approaching a similar breakdown in ocean circulation that would fundamentally alter global climate patterns. The difference is that we're pushing these systems toward collapse much faster than the geological processes that disrupted them during the ancient catastrophe. Ice sheet dynamics in Greenland and Antarctica are demonstrating the same kind of nonlinear acceleration that characterized other aspects of the Carnian crisis. Traditional ice sheet models assumed that melting would occur gradually as temperatures rose. Instead, recent observations show ice loss accelerating exponentially as feedback mechanisms kick in that weren't included in earlier projections. The surface of the Greenland ice sheet is darkening as dust and soot from human activities accumulate on the ice. This darker surface absorbs more solar radiation, accelerating melting in a positive feedback loop that becomes self-reinforcing. Meltwater creates pools on the surface that absorb even more heat, drilling down through the ice sheet and lubricating the base, causing entire sections to slide toward the ocean faster than previously thought possible. Antarctic ice dynamics are even more concerning because the ice sheets there are much larger, and their collapse could contribute to sea level rises measured in tens of feet rather than inches. Recent studies of Antarctic ice shelves show that warming ocean water is melting them from below, reducing their ability to hold back the massive glaciers that flow toward the sea. Once these ice shelves collapse, the glaciers they're restraining could flow into the ocean at rates that would raise global sea levels catastrophically within decades. The speed of current ice sheet changes rivals what occurred during the most rapid ice melting events in Earth's history. The difference is that those ancient rapid melting events occurred during natural climate transitions that took thousands of years to develop. Current ice loss is occurring during a climate transition that we're creating over mere decades, compressing the same physical processes into timescales that give coastal civilizations no time to adapt. Urban areas around the world are already experiencing the early effects of these accelerating changes. Heat island effects that make cities significantly hotter than surrounding areas are being amplified by rising global temperatures. Some cities are experiencing heat waves that exceed the tolerance limits of human physiology for extended periods. These extreme heat events aren't isolated incidents, but represent the new normal as temperature distributions shift beyond historical ranges. Infrastructure systems designed for 20th century climate conditions are failing under 21st century weather extremes. Power grids are experiencing cascading failures as heat waves increase demand while simultaneously reducing transmission efficiency. Transportation networks are being disrupted by temperature extremes that cause materials to expand beyond design specifications. Water treatment and distribution systems are being overwhelmed by extreme precipitation events that exceed their processing capacity. Agricultural regions that have fed human civilization for thousands of years are experiencing crop failures as temperature and precipitation patterns shift beyond the tolerance ranges of traditional food crops. Some of the world's most productive farming areas are becoming unsuitable for agriculture as heat stress and changing rainfall patterns make it impossible to maintain the yields that global food security depends on. The speed of these agricultural impacts is particularly alarming because food security operates on annual cycles that give societies very little time to adapt to changing conditions. A single bad growing season can trigger food shortages that affect millions of people. Multiple consecutive years of climate-disrupted agriculture could trigger famines that destabilize entire regions. Migration pressures created by these rapid environmental changes are already beginning to strain political and social systems around the world. Climate refugees aren't a future problem. They're a current reality that's growing exponentially as more regions become uninhabitable due to extreme heat, flooding, drought, or sea level rise. The scale of potential climate migration could dwarf any previous human population movements. Coastal megacities that house hundreds of millions of people face the prospect of regular flooding within decades as sea levels rise and storm surges intensify. The infrastructure investments required to protect these population centers exceed the economic capacity of most nations. Some communities are already beginning planned retreats from coastlines that are becoming uninhabitable. Water resources that have supported human settlements for millennia are being disrupted faster than alternative sources can be developed. Aquifers that took thousands of years to fill are being drained within decades as surface water becomes unreliable and demand increases due to heat stress. Some regions face the prospect of becoming uninhabitable simply due to lack of accessible fresh water. The economic systems that support modern civilization assume climate stability in ways that are becoming increasingly unrealistic. Insurance markets are withdrawing from regions that face increasing climate risks. Financial institutions are beginning to factor climate change into long-term investment decisions. Supply chains that depend on predictable seasonal patterns are being disrupted by extreme weather events. These economic impacts create their own feedback loops that accelerate social and political instability. Regions that can no longer attract investment due to climate risks face economic decline, reduces their ability to adapt to changing conditions. Wealthy areas that can afford climate adaptation measures become increasingly isolated from regions that lack such resources. International cooperation that's essential for addressing global climate challenges is being undermined by the very climate impacts that make cooperation necessary. Resource scarcity and migration pressures create conflicts that make it more difficult to coordinate global responses to climate change. The window for preventing catastrophic climate change is closing at the same time that political conditions are making decisive action more difficult. The psychological impact of these rapid changes is creating a form of collective trauma that affects decision-making at every level of society. Climate anxiety is becoming a widespread mental health issue as people struggle to process the implications of environmental changes that are occurring faster than human psychology evolved to handle. The speed of change is overwhelming the cognitive systems that humans use to plan for the future and make long-term decisions. Educational institutions designed to prepare students for predictable career paths are struggling to adapt to a future that may be fundamentally different from anything in human experience. Skills and knowledge that were valuable for previous generations may become obsolete as climate changes disrupt the economic and social systems that created traditional career opportunities. Research institutions that normally operate on timescales of years or decades are being forced to accelerate their work to keep pace with changes that are occurring faster than scientific publishing cycles can document. The peer review processes that ensure scientific accuracy are being strained by the urgency of understanding changes that are happening in real time. Military and security organizations around the world are recognizing climate change as a threat multiplier that could destabilize regions and create conflicts that exceed their capacity to manage. Traditional concepts of national security become inadequate when facing environmental changes that don't respect national borders and can't be deterred through conventional means. The speed of current changes is creating a situation where every institution that humans have developed for managing long-term challenges is being overwhelmed by the pace of environmental transformation. Governments, markets, educational systems, and international organizations all assume that change occurs gradually enough for adaptation and planning. Climate change is violating these assumptions in ways that could undermine the institutional foundations of modern civilization. The Carnian pluvial episode demonstrates what happens when Earth's climate system crosses thresholds that trigger rapid transitions to new stable states. The geological record shows that once these transitions begin, they become self-sustaining through feedback mechanisms that operate independently of the original triggers. The system finds a new equilibrium point that can persist for millions of years, even after the conditions that created the transition have changed. We may be approaching similar thresholds today, but with changes occurring so rapidly that we could cross multiple tipping points simultaneously before any individual system has time to stabilize. The cumulative effect could trigger climate changes that are more extreme and longer lasting than anything in the geological record. The difference between our situation and the Carnian catastrophe isn't just the speed of change, it's also the starting point. The Carnian crisis began from atmospheric conditions that had been relatively stable for millions of years. We're starting from a climate system that's already been destabilized by more than a century of industrial emissions and is now being pushed at unprecedented rates toward conditions that complex life has never experienced. Current atmospheric CO2 levels are higher than they've been for over 3 million years, before the evolution of modern ecosystems and long before the emergence of human civilization. We're conducting an experiment with atmospheric composition that has no precedent in the history of complex life on Earth. The results of this experiment will determine not just the future of human civilization, but the evolutionary trajectory of life itself for millions of years to come. The Carnian period shows us that Earth's climate system can remain stable for vast periods of time, then suddenly shift to completely different configurations that persist for equally vast periods. These transitions aren't gradual adjustments that allow time for adaptation. They're rapid reorganizations of planetary systems that create new rules for how Earth operates. We're approaching the kind of atmospheric conditions that could trigger such a transition, but we're doing so faster than any natural process in the geological record. The question isn't whether Earth's climate can change dramatically. The evidence proves it can. The question is whether human civilization can survive the kind of rapid, extreme changes that occur when atmospheric composition is altered as quickly as we're currently changing it. The rain that fell continuously for 2 million years during the Carnian period wasn't just unusual weather, it was evidence of a planet operating under completely different physical rules, sustained by atmospheric and oceanic processes that had no equivalent in Earth's previous history. The same forces that created those alien conditions are building in our atmosphere today, compressed into timescales that make the ancient catastrophe seem gradual by comparison. We have the knowledge to understand what's happening and the technology to change course, but the window for action is closing faster than most people realize. The climate system doesn't wait for human institutions to reach consensus or for economic conditions to be favorable for change. It responds to atmospheric composition according to the laws of physics, regardless of human preferences or political considerations. The choice we face is whether we'll learn from the most extreme climate catastrophe in Earth's history before triggering our own version of the same fundamental breakdown. The geological record offers us a preview of what lies ahead if we continue on our current trajectory. The question is whether we're wise enough to heed these warnings before discovering firsthand what it means to live through a climate transition that could make the ancient catastrophe seem mild by comparison. The story of the Carnian pluvial episode forces us to confront a reality that's almost too vast for human comprehension. We've traced this ancient catastrophe from its volcanic origins through 2 million years of relentless precipitation, witnessing how it reshaped evolution itself and set the stage for the rise of dinosaurs. We've examined the geological evidence preserved in rocks around the world, the chemical signatures that prove this impossible event really occurred, and the biological innovations that emerged from the crucible of endless rain. But the most chilling revelation isn't what happened 232 million years ago. It's happening right what's now. The same that trigger atmospheric processes, the most extreme weather event in Earth's history, are operating in our skies today, into timescales that make the ancient compressed volcanic seem gradual by comparison. We're emissions the not just approaching conditions that created the Carnian nightmare. We're racing toward them at speeds that dwarf anything in the geological record. Every data point tells the same story. Atmospheric carbon dioxide levels rising faster than any natural process in Earth's history. Permafrost releasing stored greenhouse gases at exponentially accelerating rates. Ocean circulation systems showing signs of impending collapse. Ice sheets melting at rates that could raise sea levels catastrophically within decades rather than centuries. The Amazon rainforest transitioning from carbon sink to carbon source. Each of these systems represents a potential tipping point that could trigger cascading changes throughout Earth's climate system. The feedback mechanisms that sustained the Carnian crisis for millions of years are already activating in our modern world. Arctic sea ice disappearing faster every year, exposing dark ocean water that absorbs heat instead of reflecting it back to space. Extreme weather events parking over regions for weeks at a time, creating heat domes and atmospheric rivers that exceed anything in recorded history. Agricultural systems failing as temperature and precipitation patterns shift beyond the tolerance ranges of crops that have fed civilization for millennia. Urban infrastructure designed for historical climate patterns is being overwhelmed by weather that exceeds every design specification. Coastal cities face regular flooding as sea levels rise and storms intensify. Water resources that sustained human settlements for thousands of years are becoming unreliable as precipitation patterns become increasingly chaotic. Economic systems that assume climate stability are being disrupted by changes that are accelerating faster than societies can adapt. The speed of these transformations reveals something terrifying about our current trajectory. We're conducting an uncontrolled experiment with the only planet we have, pushing atmospheric composition toward levels that haven't existed since long before complex life evolved on Earth. The volcanic emissions that triggered the Carnian catastrophe continued for millions of years, but they started from atmospheric conditions that had been relatively stable for geological ages. We're beginning from a climate system that's already been destabilized and pushing it harder and faster than any natural process in Earth's history. Climate scientists studying ancient analogues like the Carnian period have discovered that Earth's climate system can remain stable for millions of years, then suddenly flip to completely different configurations within just a few thousand years. Once these transitions occur, returning to previous conditions requires changes that take geological timescales to develop. The system finds new equilibrium points that can persist for millions of years, sustained by feedback mechanisms that operate independently of whatever originally triggered the change. This understanding reveals the true stakes of our current situation. We're not just facing the possibility of gradually warming temperatures or slowly rising sea levels. We're potentially approaching thresholds that could trigger rapid transitions to climate states that would persist for geological ages. The same physics and chemistry that created 2 million years of continuous rain operate in our atmosphere today. The only difference is the speed, and that difference might make our situation even more dangerous than the ancient catastrophe. Modern computer models incorporate many of the same processes that operated during the Carnian period, but they may not fully capture the potential for non-linear changes when multiple systems reach tipping points simultaneously. The geological record suggests that climate transitions can occur much more rapidly than gradual projections indicate, especially when atmospheric composition changes as quickly as we're currently altering it. The biological implications of such rapid changes extend far beyond simple species extinction. The Carnian period demonstrates that extreme climate events don't just stress existing ecosystems. They fundamentally alter the evolutionary trajectory of life itself. The species that survived the ancient catastrophe were those that could adapt quickly to completely novel environmental conditions. Specialists that had evolved to thrive in specific environments were often the first casualties when those environments disappeared overnight in geological terms. This pattern has profound implications for our current biodiversity crisis. We're not just facing the loss of individual species or ecosystems. We're potentially facing changes that could alter the entire future of evolution on Earth. The organisms that survive whatever climate changes lie ahead may be fundamentally different from those that exist today, shaped by selective pressures that have no precedent in the evolutionary history of complex life. Conservation strategies developed for gradual environmental change may be inadequate for the rapid transitions we're potentially approaching. Protecting existing species and habitats, while important, may be insufficient if environmental conditions shift faster than natural adaptation processes can operate. The genetic and ecological diversity that provides raw material for evolutionary adaptation becomes crucial when facing unprecedented environmental pressures. The Carnian period also reveals the interconnected nature of all Earth systems in ways that make simple solutions to climate change seem naive. The ancient catastrophe affected not just atmospheric composition and weather patterns, but ocean circulation, soil chemistry, plant communities, animal behavior, and evolutionary processes. Changes in one component cascaded through every other system, creating feedback loops that amplified and sustained the crisis for millions of years. Modern Earth system science recognizes these same interconnections operating today. Atmospheric changes affect ocean chemistry, which influences marine ecosystems, which alter carbon cycling, which feeds back into atmospheric composition. Terrestrial ecosystems respond to changing precipitation patterns by shifting their carbon and storage release, which further influences atmospheric greenhouse gas concentrations. The complexity of these interactions makes predicting specific outcomes difficult, but it also suggests that the potential for cascading changes is enormous. Recovery from the Carnian crisis required the coordinated reconstruction of multiple Earth systems over millions of years. New atmospheric circulation patterns had to develop that could function with altered geography and ocean chemistry. Marine ecosystems had to evolve that could operate under different temperature and chemical conditions. Terrestrial communities had to adapt to novel precipitation patterns and soil conditions. This recovery process took geological ages precisely because so many interconnected systems had to be rebuilt simultaneously. Understanding this complexity is crucial for grappling with current climate challenges. Solutions that focus on single aspects of the problem may be insufficient if other components of the Earth system have already been destabilized. The Carnian period suggests that once certain thresholds are crossed, recovery requires coordinated changes across multiple systems that can take millions of years to accomplish. The acceleration of current environmental changes creates additional challenges that the ancient world never faced. The Carnian crisis unfolded over thousands to millions of years, providing at least some time for evolutionary and ecological adaptation. Current changes are happening over decades, potentially giving natural systems no time to adjust before being overwhelmed by the next wave of environmental transformation. This temporal compression affects every aspect of how Earth systems respond to change. Evolutionary processes that normally provide biological adaptation operate over thousands of generations. Soil formation processes that create the foundation for terrestrial ecosystems require centuries or millennia. Ocean circulation adjustments that redistribute heat around the planet take decades to centuries to complete. When environmental changes occur faster than these natural response times, systems can be pushed beyond their ability to maintain stability. The psychological and social dimensions of rapid climate change create additional feedback loops that can either help or hinder adaptation efforts. Climate anxiety and despair can paralyze decision-making processes at individual and collective levels. Alternatively, recognition of the urgency and magnitude of climate challenges can mobilize unprecedented cooperation and innovation. The social response to climate change becomes a crucial factor in determining whether human societies can navigate the transitions ahead. Educational systems designed to prepare people for predictable futures face fundamental challenges when the future becomes radically uncertain. Traditional approaches to career planning, economic development, and social organization assume degrees of environmental stability that may no longer exist. Preparing for an uncertain future requires different skills and mindsets than preparing for predictable career paths in stable environments. International cooperation becomes both more necessary and more difficult as climate impacts intensify. Global challenges require coordinated responses that transcend national climate boundaries and political divisions, yet impacts create resource themselves, scarcities and make and migration pressures that can increase conflicts, cooperation more difficult to achieve. The window is closing at the same time that political for preventing catastrophic changes conditions are making decisive action more challenging. The technological capabilities that could help address climate challenges exist today in ways that weren't available during previous climate transitions. Renewable energy systems, carbon capture technologies, and advanced materials science provide tools for reducing emissions and adapting to changing conditions. However, deploying these technologies at the scale and speed required to prevent catastrophic changes requires social and political transformations that may be as challenging as the technological development itself. Economic systems that assume infinite growth on a finite planet face fundamental contradictions when confronted with planetary boundaries and climate constraints. Traditional measures of economic success may become counterproductive when they encourage activities that destabilize the environmental conditions that make economic activity possible. Developing new economic models that operate within planetary constraints while meeting human needs represents one of the greatest intellectual challenges of our time. The moral dimensions of climate change extend across generations and species in ways that challenge traditional ethical frameworks. Decisions made today will influence environmental conditions for thousands of future generations. The impacts of current emissions will persist in the atmosphere and oceans long after the people making those decisions have died. This temporal extension of moral responsibility creates ethical obligations that exceed anything previous generations have faced. Indigenous communities around the world often possess traditional knowledge about living with environmental variability that could inform adaptation strategies for rapid climate change. These knowledge systems evolved over thousands of years of direct experience with environmental fluctuations and often emphasize resilience and flexibility rather than control and prediction. Integrating traditional ecological knowledge with modern science could provide insights into how human societies might navigate unprecedented environmental changes. The Carnian pluvial episode ultimately stands as both a warning and a testament to the resilience of life on Earth. It shows us that our planet can survive even the most extreme environmental catastrophes, but it also reveals the enormous costs of such survival. The Earth that emerged from the ancient crisis was profoundly different from the one that entered it, and those changes persisted for geological ages. The 2 million years of continuous rain weren't just unusual weather. They represented a complete reorganization of how Earth operated, triggered by changes in atmospheric composition that may have been no more dramatic than what we're causing today. The geological record preserves the moment when our planet crossed a threshold that transformed it into something that would have been utterly alien to any observer from previous eras. We stand at a similar threshold today, but with the advantage of understanding what lies beyond it. The choice we face is whether we'll learn from this ancient catastrophe before triggering our own version of the same fundamental forces. The rain that fell for 2 million years straight serves as the ultimate demonstration of what happens when Earth's climate system is pushed beyond its breaking point. The evidence is overwhelming, the parallels are undeniable, and the timeline for action is shrinking faster than most people realize. We have the knowledge to avoid repeating this ancient nightmare, but only if we act quickly enough to prevent crossing the atmospheric thresholds that could transform our world into something as alien as the planet that once experienced endless rain for geological ages. The question that will define the future of human civilization is whether we're wise enough to heed the warnings written in stone from 232 million years ago, or whether we'll discover firsthand what it means to live through the most extreme weather event our planet has ever experienced. The story of the Carnian pluvial episode isn't just a fascinating glimpse into our planet's ancient past. It's a mirror reflecting our present moment and a window into what might be our future. 2 million years of continuous rain transformed Earth into an alien world, reshaped the entire trajectory of evolution, and demonstrated the terrifying power of runaway climate change. But perhaps most importantly, it shows us exactly what happens when atmospheric composition crosses certain critical thresholds that lock our planet into extreme states for millions of years. The parallels to our current situation aren't just striking, they're undeniable. The same volcanic emissions that triggered the ancient catastrophe are being matched by human industrial activity today, but compressed into timescales that make the geological processes seem gradual by comparison. The feedback mechanisms that sustained those impossible conditions for geological ages are already activating in our modern world. From melting permafrost to collapsing ice sheets to dying forests that once helped stabilize our climate. The geological record has given us the ultimate warning. It's shown us that Earth's climate system can flip like a switch from stable conditions to catastrophic extremes that persist for millions of years. The transition happens faster than anyone expects, and once it begins, returning to normal conditions requires changes that take geological ages to develop. We have something the organisms of 232 million years ago didn't have. We have the knowledge to understand what's happening, the technology to change course, and the ability to learn from the most extreme climate event in Earth's history. But that knowledge only matters if we act on it before we cross the same thresholds that once transformed our planet into a world where the sun disappeared and the rain never stopped falling. The choice is ours, but the window for making that choice is closing faster than we ever imagined. The question isn't whether Earth's climate can change dramatically. The Carnian period proves it can. The question is whether we're wise enough to prevent our own version of the catastrophe that once made rain fall continuously for 2 million years straight.